specific elements rather than looking at results for the whole model. But for the moment, those of you who had 0 results displayed from last week, just click on that icon and make sure the model is set to display. You should see your result.
And this model was actually one of these. Yes.
Okay, so we'll go back to the model we had last week, and you may remember we just set up the basic model, we put in the beam properties, but we didn't set up any locations. So that's what we need to do this week. First thing we need to do is make sure our beam properties are correct in terms of the density, so such self-weight calculation will be correct. If we go and look in the under property, beam, we'll start with the main longitudinal precast beams, and the density in there at the moment is 2.4, which is the default number from the standard materials. And that's, in this case, isn't going to be exactly right. And there are 2 reasons for that. First is that the calculated mass of the element is based on the cross-section that we put in. And you remember for the top slab, we make that actually, we reduce the width because the top slab concrete is a lower grade than the precast concrete. So to get the stiffness of the section right, we actually reduce the width of the top slab. So that means the calculated weight is going to be too low. So we've actually got to calculate an effective density to account for that reduction in the area. The other thing is that the thickness of the top slab we put in as 200 millimeters, which is the theoretical area, so that's the minimum depth as shown on the drawings. So for calculating the section properties, that's the right thing to do. But with these precast beams, because of the pre-tensioning, when they're placed on site without the in-situ concrete on top, they don't come out straight, they actually have a hog curve. And that hogging can be about 30-40 millimeters typically. So it means when you pour the top slab on top, it won't be a constant thickness. It'll actually vary, but the minimum will be 200 millimeters. So the actual thickness as constructed will be something greater than 200 millimeters. So we have to do a calculation or make an estimate of what the average thickness will be, and then use that to calculate the correct area, and then adjust the density to give us the final correct weight. Now I've got a spreadsheet with that calculation on. We'll have a look at that more closely next week. But for today's purposes, all we need to do is go into here and in density increase that value to 2.85. So that's the calculated effective density to take account of the fact that our cross-section area is not quite right. Okay? So that's beam property 1, which is the longitudinal precast beams. Beam property 2 is the end diaphragms, which is in situ concrete. In that case, we put in the cross-sectional shape ourselves, so we don't need to adjust that. But the standard density for concrete, like they have in the standard properties, 2.4 tonnes per cubic metre, is actually a bit on the low side. And the reason for that is that's the weight for concrete, but our concrete has actually got a lot of reinforcement in it. Steel is a lot heavier than concrete. So a typical average density is 2.5 tonnes per cubic metre rather than 2.4. So we'll change beam property 2 density to 2.5. And then finally beam property 3. Again, we've got a density of 2.4 in there. But if we look at the model, we can see we've got our longitudinal beams, which already include the weight of the top slab. So we need to put in the cross beams to model the stiffness of the top slab, because in our model the longitudinal beams are not connected. So we need to connect them together. But those green cross beams are only there so we're connecting those longitudinal beams together. If we put a density into those cross beams, we're actually counting the top slab twice, which we don't want to do. So we need to go into the property, beam type 3, and set that to 0. Okay, so just to run through that again, the beam type 1 includes the precast beams plus the top slab, and we've adjusted the weight to allow for the area of our cross section not being exactly what will be built on site. Beam type 2, we've increased the density to allow for the fact that the reinforced concrete includes steel as well as concrete. And beam type 3 we've set to 0 because we've already allowed for the weight of the in situ concrete. Okay, so that's the beam properties. Now we need to set up some load cases, which is similar to what we did for the pier analysis. So got a global load and freedom cases. And then we create some new cases with this icon, new case, and we can give each of those a description to say what they are. So click on the edit icon up there. So the first one is self-weight. Next one is SDL, that's superimposed dead load. And that's the surfacing. So typically bridges in Australia who have a concrete top slab, then on top of that there's usually an asphalt surface, not always, but usually. It varies in different countries. Typically in the USA, they run directly on top of the concrete. In Australia they usually put an asphalt surface which gives a better riding surface. So load case 2 is for the weight of that. Load case 3 is for SDL again, median. So if you recall, the cross section of this bridge has got 2 carriageways, and down the middle there's a medium strip, concrete small barrier between the 2 carriageways, so we need to account for the weight of that. And then the final SDL case is for the barriers at the edge of the deck. Okay, so the last one, this week we're just going to put in one live load case. Next week when we look at the live load in more detail, we'll generate a lot more cases because we need to find the position of the live load vehicles, which gives the worst effects both for bending moments and for shear forces. But for this week we'll just have the one case. Okay, so just going back in there, just a reminder that we should have set this up last week. For the self weight, we've got a gravity load, acceleration due to gravity there, minus direction because it's downwards, and that should be in the Z direction because our bridge deck is modelled in the XY plane, so the Z direction is down. Minus Z is downwards. The other load cases should have no gravity load. Because we don't want to count it twice, okay?
That's it, yeah.
Okay, so to assign some loads for those load cases, we click on this tab at the top left and select the load case we want. And I'm just going to look at the example from last year to remind myself what the values we used were. If you make a note of these values for this afternoon, and then next week's lecture we'll look at in more detail about how we arrive at these numbers. So we've got for the surfacing we've got 4.4 kilonewtons per metre, which is applied as load to for all the longitudinal beams. I'll go back to my model, and the easiest way to apply to a particular type of beam, right click and go to show by type property and select the beam you want. Okay, so now I can press Control A and go to attribute beam distributed load, Force Global.